Today we will learn tension test. Aim to determine ultimate tensile stress of a metal. Objective to conduct a tensile test on a mild steel specimen and determine the following: 1. Limit of proportionality. 2. Elastic limit. 3. Yield strength. 4. Ultimate strength. 5. Young's modulus of elasticity. 6. Percentage elongation. 7. Percentage reduction in area. Apparatus required: 1. Universal testing machine UTM. 2. Mild steel specimens. 3. Graph paper. 4. Scale. 5. Vernier caliper. This figure shows you the diagram of universal testing machine UTM. Parts of universal testing machine: upper crosshead, columns, tension test specimen, middle crosshead, space for compression test, lower crosshead, positioning screws, base servo motor and system. Upper figure shows you specimen with circular X section and lower figure shows you specimen with rectangular X section. Theory: the tensile test is most applied one of all mechanical tests. In this test, ends of test piece are fixed into grips connected to a straining device and to a load measuring device. If the applied load is small enough, the deformation of any solid body is entirely elastic. An elastically deformed solid will return to its original form as soon as load is removed. However, if the load is too large, the material can be deformed permanently. The initial part of the tension curve, which is recoverable immediately after unloading, is termed as elastic, and the rest of the curve, which represents the manner in which solid undergoes plastic deformation, is termed as plastic. The stress below which the deformation, essentially entirely elastic, is known as the yield strength of material. In some material, the onset of plastic deformation is denoted by a sudden drop in load indicating both an upper and a lower yield point. However, some materials do not exhibit a sharp yield point. During plastic deformation at large extensions, strain hardening cannot compensate for decrease in section, and thus the load passes through a maximum and then begins to decrease. This stage, the ultimate strength, which is defined as the ratio of the load on the specimen to original cross-sectional area, reaches a maximum value. Further loading will eventually cause neck formation and rupture. Procedure 1. Measure the original length and diameter of the specimen. The length may either be length of cross section, which is marked on the specimen with a preset punch, or the total length of the specimen. 2. Insert the specimen into grips of the test machine and attach strain measuring device to it. 3. Begin the load application and record load versus elongation data. 4. Take readings more frequently as yield point is approached. 5. Measure elongation values with the help of dividers and a ruler. 6. Continue the test till fracture occurs. 7. By joining the two broken halves of the specimen together, measure the final length and diameter of specimen. Description of UTM and extensometer. Loading unit. It consists of main hydraulic cylinder with robust base inside, the piston which moves up and down, the chain driven by electric motor which is fitted on left hand side. The screw column maintained in the base can be rotated using above arrangement of chain. Each column passes through the main nut which is fitted in the lower crosshead. The lower table connected to main piston through a ball, and the ball seat is joined to ensure axial loading. There is a connection between lower table and upper head assembly that moves up and down with main piston. The measurement of this assembly is carried out by number of bearings which slides over the columns. The test specimen each fixed in the job is known as jack job. To fix up the specimen tightly, the movement of jack job is achieved helically by handle. Control panel. It consists of oil tank having a hydraulic oil level side glass for checking the oil level. The pump is displacement type piston pump having free plunger, those ensure for continuation of high pressure. The pump is fixed to the tank from the bottom. The suction and delivery valve are fitted to the pump near 10 electric motor driven. The pump is mounted on 4 studs, which is fitted on the right side of the tank. There is an arrangement for loosening or tightening of the valve. The 4 valves on control panel control the oil stroke in the hydraulic system. The loading system works as described below. The return valve is closed, oil delivered by the pump through the flow control valves to cylinder, and the piston goes up. Pressure starts developing and either the specimen breaks or the load having maximum value is controlled with the base dynamometer consisting in a cylinder in which the piston reciprocates. The switches have upper and lower push at the control panel for the downward and upward movement of the movable head. The on and off switch provided on the control panel and the pilot lamp shows the transmission of main supply. Method of testing. Initial adjustments. Before testing, adjust the pendulum with respect to capacity of the test, that is 8 tons, 10 tons, 20 tons, 40 tons, etc. For example, a specimen of 6 tons capacity gives more accurate result of 10 tons capacity range instead of 20 tons capacity range. These ranges of capacity are adjusted on the dial with the help of range selector knob. The control weights of the pendulum are adjusted correctly. The ink should be inserted in pen holder of recording paper on the drum and the testing process is started depending upon the types of tests. Extensometer. This instrument is an attachment to universal oblique tensile testing machines. This measures the elongation of a test place on load for the set gauge length, the least count of measurement being 0.01 mm and maximum elongation measurement up to 3 mm. This elongation measurement helps in finding out the proof stress at the required percentage elongation. Working of the instrument. The required gauge length between 30 to 120 is set by adjusting the upper knife edge. 3A scale 2 is provided for this purpose. Hold the specimen in the upper and lower jaws of tensile oblique universal testing machine. Position the extensometer on the specimen. Position upper clamp 4 to press upper knife edge on the specimen. The extensometer will be now fixed to the specimen by spring pressure. Set 0 on both the dial gauges by 0, adjust screw 7. Start loading the specimen and take the reading of load on the machine at required elongation or the elongation at required load. Force setter accuracy mean of both the dial gauge 8 readings should be taken as elongation. It is very important to note and follow the practice of removing the extensometer from the specimen before the specimen breaks, otherwise the instrument will be totally damaged. As a safety, while testing the instrument may be kept hanging from a fixed support by slightly loose thread. Figure shows you stress-strain graph of mild steel. This figure shows you stress-strain graph of different materials. Curve A shows a brittle material. This material is also strong because there is a little strain for high stress. The fracture of a brittle material is sudden and catastrophic with little or no plastic deformation. Brittle materials crack under tension and the stress increases around the cracks. Cracks propagate less under compression. Curve B is a strong material which is not ductile. Steel wires stretch very little and break suddenly. There can be a lot of elastic strain energy in steel wire under tension, and it will whiplash if it breaks. The ends are razor sharp and such a failure is very dangerous indeed. Curve C is a ductile material. Curve D is a plastic material. Notice a very large strain for a small stress. The material will not go back to its original length. Unit of proportion is equal to load at limit of proportioning divided by original area of cross section. Elastic limit is equal to load at elastic limit divided by original cross sectional area in Newton per mm square. Yield strength is equal to maximum tensile strength divided by original area of cross section. Young's modulus is equal to stress below proportionality divided by corresponding stress. Percentage of elongation is equal to final length at fracture, original length divided by original length. Percentage of reduction in area is equal to original area at fracture divided by original area.